Okay, here's some questions where you're asked to rationalize the denominator. In this case, there's only one term in the denominator, and if there's just one term in the denominator, you don't have to multiply by the conjugate. But what you're wanting to do is to multiply it by something so you can get rid of the radical. Now I know if I had like the square root of 4, that comes out to 2, radical's gone. If I have the square root, say, of 6, what I could do is I could multiply, what could I go by? Maybe I could multiply by this, I could multiply by the square root of 6. So there's 2 6's, that'll give me the square root of 36, which is just 6. Again, I'm wanting to just get a number at the bottom without a radical. If they have the cube root, what they're looking for is 3 identical numbers inside that you can bring one out. That's one way of looking at it. The other way of looking at it is you're trying to get a perfect cube. Like if I'm dealing in the square root realm, I can get 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, etc. Those are the numbers I'm looking for to get underneath the radical so that I can get rid of the radical. If I have the cube root, these are the numbers you're looking for. 1, 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 cubed 125. That's probably where I'm headed there. 6 cubed, I think it's 216. 7 cubed, I don't know, 289 maybe. 8 cubed 256. That can't be 289. 8 cubed. Anyway, you go 8 times 8 times 8. I'm not sure about these ones. Anyway, with 25, what I'm wanting to do is I'm wanting to get to 125. So I'm going to take the cube root of 25, and I'm going to multiply top and bottom by the cube root of 5. Because on the bottom, when I multiply by the cube root of 5, I'm going to get the cube root of 125, which is one of those perfect cube roots. On the top, I'm left with 3 times the cube root of 5. But on the bottom now, the cube root of 125 is just plain 5. And then on the top, I have 3 cube root 5. So that's how you go about doing those. If you wanted to try the other questions that I'm going to show you here, try them on your own and come back and see if you can get. Okay, so this one, cube root 4 over cube root 6. So I'm going to use that cube root rule. I forget what it's called, but it says you can separate those. So you can call it the cube root of 4 divided by the cube root of 6. And now what I want to get on the bottom is one of those perfect numbers again. So 1 cubed is 1, 2 cubes 8, 3 cubed, 4 cubed, 5 cubed, 6 cubed I think is 216. Let's see, 36 times, that's 36, 3, yeah, it's 216. So I want to get 216. So I'm going to multiply both top and bottom by the cube root. I have to get 216. So whatever 216 divided by 6 is, I think it comes out to 36. So top and bottom I multiply by the cube root of 36. On the top I'm going to get cube root of 4 times 36, whatever that comes out to. I think 144. All over the cube root of 216. 6 times 36 is 216. Cube root of 16 is just plain old 6. Good. Now cube root of 144, I might be able to simplify that. Like 144, I know is 36 times 4. And 36 is 9 times 4. I can't get 3 4s, but maybe I can get 3 2s. 4 is 2 times 2. The other 4 is 2 times 2. And there's a perfect cube root. So I could rewrite the cube root of 144 as the cube root of 2 times 2 times 2 is 8. times the cube root of 9 times 2 would be 18. Okay, now I'm doing that because the cube root of 8 is 2, and then I can probably simplify that with the 6 on the bottom. So 2 goes into once and into 6 3 times, so the answer is cube root of 18 divided by 3. Love to be able to divide the 3 into the 18, but one's in a radical, one's out, so you can't. So I'd probably stop there. Now the other thing that I just noticed that I should have done maybe right off the bat is simplify. This fraction, I could have simplified it. Let me do that here in blue. So I could have written it as, like 2 goes into there twice and into there 3 times. So I could have written it as cube root of 2 over the cube root of 3. Is that right? Yeah. So then I would multiply the bottom by the cube root of 9, because that'll get me to 27. And if I do that on the bottom, I have to do that on the top. So on the top, I'll be left with cube root of 2 times 9 is 18. And on the bottom, I'll have the cube root of 27, which is just plain 3. So I get the same answer. I just didn't get to do all this fun work. That would have been smart to do that at the start. Last one. Ooh, this one's a little easier because there's no cube root on the top. So I have 4, and on the bottom I have the cube root of 49. I'm just going to express as 7 times 7. And x squared I'm going to express as x times x. If I have the cube root, I need 3 things inside to be able to take one out. Or like 7 times 7 times 7, I think is 349. I forget what. I've got to figure that out. 49 times 7. Oh, it's not even 49 at all. 9 times 7 is 63. 6, 343. Whatever. So I'm wanting to get to 343. So what I can do is I can multiply the top by the cube root of 7 and multiply the bottom by the cube root of 7, because 7 times 7 times 7 will give me that 343, and that's a perfect cube root. Now x's, there's 2 x's here. I have to get rid of x's 2 out of the radical. There's 2, so I'm going to multiply top and bottom by an additional x. So on the top, and I'm going to write an extra step, but I probably wouldn't normally write this. On the top I have 4 cube root 7x. On the bottom I have the cube root of 7 times 7 times 7 times x times x times x. Cube root of 7 times 7 times 7 is just plain 7. Cube root of x times x times x is just plain x. No cube root, no radical at all. And then on the top I have 4 cube root 7x. Okay, hopefully that helps you with those 3 questions rationalizing denominators.